All right. So last time we were working to find out what is the average complexity for quicksort, right? So remember that we learned many different sorting algorithms, and I mean ranging from insertion sort, uh, selection sort, merge sort, heap sort, and then quicksort, right? And I mentioned that in the real world, quicksort is the fastest algorithm. And last time I mentioned a little bit about why quicksort is faster than merge sort, even though it's very similar to merge sort. So let me remind you a little bit about quicksort before we continue with solving the sum, so we can find out what is the complexity for the average case of quicksort. So let me share with you the lecture note here. I already posted online. Okay, so quicksort. First, we partition the list, right? Let's say we have a list of numbers, and then we partition it. Uh, Last time I showed you just only one algorithm. I will do it again, but the idea is that instead of partition the list into two halves, like in merge sort, right? Merge sort, partition, sort the left, sort the right, and then merge them, right? Quicksort is different. First, we partition by separating the list into two pieces. So the left will have elements smaller than the pivot, and the right will have elements bigger than the pivot, right? And then we sort the left, sort the right repeatedly using quicksort, and we don't have to merge because they are already in the right order, right? So it's different with merge sort. Merge sort means sort the left, sort the right, merge. Here, partition, sort the left, sort the right. That's it, right? Okay. Uh, and last time we learned that, so for quicksort, we don't need to have extra memory for merging, like in merge sort. That's why quicksort is faster, because we don't need to have an extra array in order to merge the results, right? All right. Now, going back to the partition algorithm. So we have first partition around the pivot. Okay. Again, the pivot last time I chose is the first element. We can have it at the last element, or we can have it randomly anywhere in the array. That's fine. Okay. Actually, if we pick the pivot, is the random value in the array is what we call the random quicksort. Okay, uh, random quicksort will help us to prevent the situation like when we have a sorted array, right? If we choose the pivot at the beginning, we are in the, say, worst case situation, right? Or if we put it at the end, and if the list is sorted in the reverse order, then we have the worst case situation. If we have the random quicksort, it avoids such kind of, say, worst case situation, but it doesn't change anything about the complexity for the average case. Yeah. All right. Now, quicksort is very simple as I'm showing you on the screen, right? Okay, and we have many different ways to partition the list. Here, I have the partition code. I call the version 1. You can see that it's a little bit different than you see in the textbook, right? In the textbook, we can choose the pivot is the last element, 5, right? But I choose this one because it's a little bit easier for me to show you how it works, right? And also the proof of the analysis of the average case, like I did here, is different than what you can find in the textbook. I believe that the proof I have here is easier to understand and to follow. Okay? If you have a chance, look at what the author has in the textbook, and you will see that from time to time I will have my own algorithm or my own proof that will help the students to understand the contents better. Okay, that's all why I spend time for doing something a little bit easier for the students. All right, now about the average case. Average case, like I showed you last time. So here is the original array, right? Average case means that we count the number of operations for all possibility and then add them up, divide by number of cases, and this is what we have for the average case for the quicksort, right? So remember that if we have n elements from 1 to n, then we have n possibilities for partitioning the list. The first possibility is that the pivot is here, the left has no element, right? And then the right has n minus 1. In this case, we have Tn is T0, right? Plus Tn minus 1. Okay? And then plus the cost for partitioning. We know that is n, right? Okay? And then the second possibility is that we have the left has one element, and then the pivot, and then the right has n minus 2, right? So in that situation, we have Tn is T1 plus Tn minus 2 plus n. And then the last situation is that the left has n minus 1, and then the right has 0 element. Here's the pivot. So in this situation, we have Tn is Tn minus 1 plus T0, right? Plus n. So here are the all possibilities when we partition and do the quicksort. So that's why we will add all of the Tn together, add on the right-hand side together, then we have the formula here for the complexity of the average case, right? So here we have n Tn, because we add all of them n times. So n Tn is the sum of Ti, right? So here we have T0 to Tn minus 1, and then T0 to Tn minus 1 again. So we have 2 times plus n squared, right? Okay, and n times. Okay. So that is what we have. And then we try to get rid of the sum, because when we learn how to solve the recurrence, we never see a situation in that we have a sum of the Ti like this. So we need to get rid of the sum. Okay? We did it by substituting n by n minus 1, subtract them, right? Simplify. Then we have here Tn divides n minus 1 less than or equal to Tn minus 1 divided by n plus here, right? So actually, this one, especially this term, is less than this term, right? It's less than 2 divided by n, right? Because the denominator is bigger, so the value will be smaller, right? So that said, instead of having 2 divided by n plus 1, we can replace this one by 2 divided by n. That's fine, right? Okay, so that's why I just want to calculate this sum. Okay, why? Let me remove this one. Okay, so here, once we have this formula, we have to solve. We need to use a substitution that instead of dealing with Tn, we deal with An. An is the left-hand side here, right? So if we define that An is Tn divided by n plus 1, then the left-hand side will become An, the right-hand side will become An minus 1 plus 2 divided by n plus 1, right? Okay, so here is something we can solve, right? Because it has n and then n minus 1. It's different with the original formula we have to solve here, right? So from here, I can write down this one as one more thing. Less than or equal An minus 1 plus 2 divided by n. Remember that 2 divided by n plus 1 is less than 2 divided by n. So An is less than or equal this. We are looking for the upper bound, or in other words, the big O, right? So from here, you already have something similar in the past. First, this one we can either use, say, double tree recurrence, okay, double recurrence tree, or you can use back substitution method. So if we use back substitution, then this one will be what? Replace An minus 1 by An minus 2, right? So it will become 2 divided by n plus 2 divided by n minus 1 plus 1, right? So that's it. Substitute this by n minus 2, right? Then you have 2 divided by n, and then 2 divided by n minus 1, etc. Okay? So continuously, we have this sum. So that is actually very similar to this, right? All we have to do is take 2 out. Right? Okay. 1 divided by I for I from 0 to n, right? Actually from 1, right? Because 1 divided by 0 is not divided, okay? Okay, now we want to solve this. In order to solve this, last time I asked you to look up the result for the integral. Yeah? The integral of 1 divided by x is what? Let me close this share screen so you can see it better. Okay. All right. So last time I asked you something like this, right? I think last time I already got an answer from one of you, that is log x, right? Okay. Natural logarithm of x. Okay. Now, how can we use this to have the result for analyzing the complexity of our algorithm here? Okay, it's very simple. Remember that the integral is nothing but the area under the curve of the function, right? Okay, that is the most important thing. So here, if you have the coordinate, the Cartesian coordinate, right? So it's the difference between mathematicians and computer scientists, right? Mathematicians love the formulas, but for computer scientists, we want to know what is the meaning and how can we use it for our purpose, for analyzing the algorithm so we can have a better algorithm. Okay. All right. So the function 1 divided by 8 divided by x is here. Right? The integral of 1 divided by x is nothing but the area under this curve. So that's said we have here. Okay. And the area we have here is log of x, okay? The natural logarithm of x. So what is the sum of 1 divided by I? Say if we have 1 here, right? 2 here. Okay. Then the sum 1 divided by I will be the area of the red rectangle here when I is 1, right? And then the area of the rectangle here when I is 2, etc. Okay? So what does it mean? The sum of 1 divided by I here, how can I compare it with the logarithm of x? What do I have? Can someone tell me? Okay, how can I compare this one and this one? Yeah, the sum is very good. The sum is always less than this, right? So this sum is less than or equal log x. Okay. All right. It's all we need. All right. So from here, we have what is AM? We have the sum here is log n. Okay, we can go it to the end, right? And that is the log of n. So log x here is from infinity, minus infinity to infinity. So that said, when we replace x by the n, then we have the sum here is less than or equal log n, right? Okay, because the x here will go from minus infinity to infinity, and we just want to go from, say, 0 to n. Okay, now from here we have an is big O log n, right? So log 2 of n or log 3 of n, they are all big O log 2 of n, right? Okay. This one, big O of log 2 of n. Okay, now let me remove this one so we can write down the solution. So from here, we have an is big O log n, right? But an is Tn divided by n plus 1, right? So we have Tn divides n plus 1 is big O log n. Hence, Tn is big O of n log n, right? N plus 1 times log n is still big O n log n, right? So that's it. And this one is the average case, the complexity of the average case for the quicksort, right? So we go from the recurrence here to this form, and then go back to Tn, and we have, say, the average case n log n. It's the same as merge sort, right? But it's faster than merge sort because we don't need the extra memory space for copying the results every time we partition, sort the left, sort the right, right? We don't need to merge. In other words, we don't need to have the extra space for writing down the sub-results. Okay, so from here, you also learn that the average case is the more accurate complexity for comparing the two algorithms. Okay, remember that for the merge sort, right, the worst case situation of quicksort is what? N squared, right? The worst case for merge sort is n log n, but the average case are the same, n log n. And when we implement quicksort is about 40% faster than merge sort for the reasons I mentioned before, that we don't need to have the extra memory space and then copying the sub results, right? Or the partial results. We don't have to do that. Okay, and that is all about quicksort. And as I mentioned before, you learn the techniques here for analyzing the average case. We will use this technique again and again in the future when we learn some advanced algorithms. Okay, the technique for getting rid of the sum is very important. Okay, so and that's why I want to use this technique instead of the proof you can see in the textbook. The proof there is good, but it involves a lot of mathematical concepts, and it will not be able to repeat that when we analyze some advanced algorithm in the future. Okay, any question about average case or quicksort? Okay, very good. Then we will go to the next topic. That is, can we say in the future be able to design an algorithm that is better than n log n as quicksort or merge sort or heap sort, right? So of course, the idea is that why sorting is important. If it's very important, then is it possible to design a better sorting, right? And of course, we can think that if I can find a faster algorithm than quicksort, then I will become very famous, right? Because everybody will use that algorithm, like Google or Facebook. All of them should have to use the new algorithm. But the question is it possible? And is what you will learn in the next lecture, right? So the short answer is no. There's no possible, there's no possible algorithm, or there is no way we can design a better than n log n sorting algorithm. Okay. Now, before we learn why, I will just give you some motivation for why sorting is that important. You have to learn so many algorithms for sorting, right? Insertion sort, quick sort, merge sort, sinking sort, bubble sort, heap sort, right? And so on. So why they are important? Can someone give me some idea about why sorting is so important? Okay, very good. Okay. If the database is sorted, then we just have to sort it once, right? Then million of people or billion of people can search the database much faster, right? Okay, very good. But here is the motivation. Let me share it with you. Okay. Okay. So the reason why we are interested with sorting algorithm dating back in 1880 when the U.S. Census had, the census, right? I think they did it again a year or two ago, right? But back to that time, the census, the consensus can be done every 10 years because it took the US Census 10 years to process the information they collected from people around the country. Okay? 10 years in order to finish the survey. Okay? Then at that time, Herman Hollerith invented a sorting algorithm. It's actually, you will learn that is what we call the bucket sort nowadays, or he invented the cat sorter. Basically, it's a sorting algorithm. Of course, when we have the U.S. census, then we have to send the mails to many households and then collect them back, right? And we have to sort the information for each person, let's say, with respect to their age, with respect to their area. You may ask, why don't we use the zip code, right? For, say, selecting the information. Why? Because we did not have the zip code back then. Okay? The zip code was very recently, I think about 1963 or so, right? We started to have the zip code. On top of that, when the US Census received the mails from households around the country, who knows which one will be sent first, which one will be sent second, right? So it means that they have a collection of the information in any order they can imagine, right? And then using the cat sorter, or basically the bucket sort, the US Census can finish the data within 6 weeks. It was a wonderful news or technology at that time. So, of course, nowadays, nobody wants to wait for 6 weeks in order to search the internet, right? So if you go to Google and then type in the search question, you have to wait 6 weeks. Nobody wants to wait for 6 weeks, right? So that's why we are very, very much interested in the sorting algorithms. So that's why so many algorithms were designed. So starting with the punch card, right? So I don't know if you use this, but when I was a student like you, I was an intern for a company, and then I actually write my, I remember that is RPG2 programs using punch card, right? Okay. Then there are many sorting machines, but nowadays with the computers, we just have to design the algorithm and have the computer run our program. It's much easier than the punch card and also the sorting machine like this, right? So we have, okay, the IBM, I think, started with some sorting machine like that. And then they grew up into a big company focusing on, say, computers like IBM machines back in 1950, 1960. Okay? So that is about the motivation for why we are interested in sorting algorithm. And now back to the question, we have merge sort, heap sort, and quick sort. The average case n log n. Okay. Also for heap sort and merge sort, the worst case is also n log n. So the question is, can we do a better job than n log n? Now let me remove the share document so we can focus on the whiteboard. Okay. All right. So now we will try to figure it out whether or not it's possible to design an algorithm that has better than n log n complexity. That also very, very helpful for us for whether or not we should spend time for doing that. It would be impossible, right? And it also tells us that analyzing the complexity of an algorithm is very important, because by analyzing the complexity, we know that whether or not the algorithm is already optimal. Yeah? If it's optimal, then we cannot do anything better than that. Okay, now let's start with one example. And then I will use the insertion sort as an illustration. I hope that you still remember the insertion sort. So now if I have a list of 3 elements, say A1, A2, and A3, it's an arbitrary list of numbers as usual, right? So when we run the insertion sort, A1, A2, A3 can be any number, right? And then we want to see with the values of A1, A2, A3, then how does the insertion sort work? Okay. So we want to see how the algorithm, in this case insertion sort, is working on an input, and then we will try to look into the details and to say, okay, what would be the complexity, okay, and what would be the worst case and best case, etc. Okay. So when we have insertion sort and we have a list of numbers like this, then what will the algorithm do first? Remember that insertion sort will work based upon the comparison of numbers, right? So what comparison the algorithm will perform first? You have 3 numbers. What number will be compared with what number when the algorithm is executed? Okay, the first and the second. Very good, right? Let me remind you a little bit, okay? So when we have a list of numbers, insertion sort will work by partition the list into 2 parts, right? The first part has 1 element and is the sorted part, and the rest is the unsorted part, right? And the algorithm will work by inserting the first element of the unsorted part into the sorted part, right? So that said, the first algorithm, the first thing the algorithm will compare is A2 and A1. All right? Okay. So now it will compare A2 and A1. A2 and A1. It will see if A2 is greater than A1. True and false. If A2 is greater than A1, then what will be the next comparison? What values will be compared next? A3 and A1. Not really. Okay. Any other idea? It's very simple. Okay. Now, after we compare A2 and A1, if A2 is greater than A1, we will not push A1 to the right, right? Okay, someone, yeah, Caleb, you have A3 and A2. Yes, that's correct. Yeah, but why? After we compare, and if A2 is greater than A1, it means that A2 is already in the right place. So we have A1, A2, and A3. And now, because A2 is greater than A1, it's already in the right place, right? So the shortest path now has A1 and A2, right? So that said, the next will be insert A3 into the sorted list here. Insert A3 by comparing with A2, right? So again, whether or not A3 is bigger than A2. Okay? Now, true and false. What will be next? What will happen if A3 is bigger than A2? It means A3, no comparison. Yes, very good. Okay, the array is already sorted, right? Because A3 is bigger, so it's A2, so it's in the right place. So that's it. This list A1, A2, A3 is sorted, right? And then we will write down here. The result is already there. Okay, I write it 1, 2, 3, meaning A1, A2, and A3. Okay, very good. Now, what happens if it's false? If A3 is not greater than A2, not really, not really. If A3 is smaller than A2, we push A2 down, right? And we are not done yet. Okay, so that's it. At this point, what we have is, okay, A1, A2, A2, right? Because remember, we push A2 to the right, and then A2, the old value is still here, right? In fact, we can write A2, or we can simply write X, because we know that this value will be replaced. Okay? So A2 will be pushed to the right, and then the place here, we will have either A1 or A3, depending on one more comparison. What's next? If it's smaller than A2, push it, right? And then compare it with A1, right? Okay. So if A3 is greater than A1, true, false. Okay, true here. What will I have? True here. What will I have here? And what does it mean with true here? If A3, okay, right here, okay, we have A3 somewhere. Let me have a different color. Remember that we have to keep A3 in a variable, right? And then compare with A2, push it if it's smaller, and now compare with A1, right? If A3 is bigger than A1, then we will write A3 here, right? Then we have what? A1, A3, and A2. Very good. 1, 3, 2. If it's false, what will I have? Three, 1, 2. Very good. Okay. Very good. Because if it's smaller, then push A1 here and write A3 here, right? 3, 1, 2. Okay. Very good. Looks like you understand the concept here, right? Now, fill out the right branch for me. I'll give you 3 minutes for doing so. Okay. What comparison and then what comparison and what results will I have if it's a false here? All right. So what do I have here for this note? Compare what number with what number? A3 A1. Very good. Whether or not A3 is greater than A1. Why? Because here at the beginning, right, we have the sorted path here, the unsorted path here. If this one is not greater than A1, meaning we have A1 pushed to the right. So we have at this point A2, A1, A3, right? And then the partition is here, right? So that said, compare A3 with A1, if it's greater than, then what will happen? True. What do I have? Okay. If A3 is greater than A1, meaning there's no pushing of the A1 and A3 is already in the right place, right? So we already have this list is sorted. So what does it mean? We have 2, 1, 3, right? So here we have 2, 1, 3. Okay? Now, if it's false, then what will happen? If it's false, compare A3 and A2, right? Okay, so it means that at this point, A3 is smaller than A1. So we push A1 to the right. So we would have what? A2 and the A1. Right? Okay. So we have A1 is pushed to the right, and then the place here will be decided by the next comparison. Right? So that said, we have to compare A3 with A2. Right? If A3 is greater than A2, true and false. What do I have for true? What do I have here? 2, 3, 1. Very good. Okay. Because A3 is greater than A2, so A3 will be written here, right? So we have 2, 3, 1. And the false. If A3 is less than A2, what do I have here? Okay, very good. Push A2, right? And then write A3. Okay, so we have 3, 2, 1. Okay, so we have all possibilities of the result. So remember that if we have n elements, then how many possible results will we have? How many possible results? In this case, I have 3, right? Then I know that I will have 6 of them. In general, if I have n elements, arbitrary, then the number of possibility is n factorial. What does it mean with n factorial? Is the number of possibility that we can shuffle the numbers here. Okay, so here I should have n factorial possibility. Here I know that 3 factorial is 3 times 2 times 1 is 6. Okay. Now 1, 2, 3, 4, 5, 6. Okay. All right. So this one is what we call a decision tree for insertion sort. Any sorting algorithm that is based on the comparison, like the algorithm you have learned so far, bubble sort, sinking sort, quick sort, merge sort, heap sort, insertion sort, selection sort, they all have a decision tree that we build based upon the results of comparison, right? And this one is called the decision tree for insertion sort. Now, for a particular input, okay, let me give you one particular input. Here, if I have 9, 4, 6, number 9, number 4, number 6, okay? How will insertion sort this array? First, it will compare A2 and A1, right? In this case, it will be false. Let me use a different color, right? And then it will compare A3 and A1. It will be false again, right? Okay? And now it will compare A3 and A2. It will be true. So the result will be here, meaning 4, 6, 9, right? So that's it. Based upon the decision tree, if we have a particular input, the algorithm will just follow one branch, starting the root to the leaf. That will give us the correct answer. So the algorithm, when we apply on a particular input, we just go through one branch. Okay? That's it. What is the complexity of this algorithm? How do I know the worst case situation for this insertion sort based upon this tree? I know that this algorithm, when we sort a list of numbers, it will have to go from the root to a leaf, right? That said, the number of comparison will be the height of the tree. I call that h. I don't know yet, but I need to find out what is h. Okay? All right. Now, if the tree has a height h, and we know that the tree here is a binary tree, right? So what would be the biggest number of leaves the tree should have? What is the biggest number of leaves? It means when the tree is full and the leaves are here on the level h, right? So the biggest number is here if the tree is full. That said, what is the biggest number of leaves? This tree should have 2 power to the h. It's the biggest number of leaves the decision tree can have, right? Okay, now, how many leaves the tree actually have? The leaves are the place where we have the result. How many of them? And factorial of them, right? So that said, we have 2 power to the h is greater than or equal and factorial. Okay? Now, how can I solve h? What is h? You can say that just take log 2 sides, right? But log of n factorial is something we cannot deal with. Okay? So it's very simple. What is n factorial? 1 times 2 times n half times n, right? Okay? Okay. Then from here, what I have? This one, if we just pay attention to, say, half number of elements, then from here I have what? If I just have n half, n half, n half, n half, right? It's greater than n half power to the n half, right? Because I simply have just n half, and then this one is n half plus 1, right? And then this one is n half plus 2 until n, right? So that said, this n factorial is greater than n half power to the n half. And now we can take the log both sides, right? So that said, h is greater than or equal n half log n half. That is n log n. Okay? Take log 2 sides. On the left-hand side, we have h. On the right-hand side, bring this one down. And then we have n half log n half, right? But n half, log n half is big O of n log n because we just remove the constant values. Okay? All right. So from here, you have the height is n log n. What does it mean? What it means from here is that for any sorting algorithm, right, we cannot have smaller than n log n for the height. Okay? If the tree has at least n log n height, then for the worst case situation, we have to go to the deepest level for the leaf, then it's already n log n, right? So the conclusion here is for any sorting algorithm, okay, the minimum complexity is, here, okay, the worst case situation is that we cannot have any shorter than n log n. Okay? That is the worst case situation. Okay. Now, if you look at the average case, it's also say that quicksort is n log n, right? And then merge sort is also n log n. But in that situation, we have to explain why quicksort is faster, right? Okay, so in that situation also, you see that the average k is not better than n log n because the height of the tree is at least n log n. The height has to be at least n log n. Okay, that's it for the insertion sort. Any questions so far about the decision tree? No question. Okay, very good. So now I can give you another exercise, right? Build a decision tree, but for the following algorithm. And again, for any algorithm, for any sorting algorithm, you have a tree that has at least n log n height. In other words, all of the algorithm will be worse than n log n or equal. Okay? You cannot design a sorting algorithm that has big O n, for example, right? Okay, later on, I will give you one sorting algorithm that is the bucket sort. And it looks like it's a big O n, but it's not if we analyze it carefully. Okay, so now the exercise build a tree here, but for selection sort. And for merge sort. Okay, use the same 3 elements array. Yes, so we have, say, 7 more minutes. So I think I can give you some hint on one of them, right? And then we'll ask you to finish it by yourself at home. Yeah. Now, selection sort is very similar to insertion sort, following the way I did here. So I believe that you will be able to finish this. But merge sort is a little bit different. So I will help you with building the decision tree for merge sort. Okay? Now, I will give you, say, 3 minutes to work on the decision tree for merge sort, and then I will ask you what comparison will be performed first. Okay, for merge sort, what value will be compared with what value first at the root of the tree. Okay, 3 minutes, so we can talk about the merge sort. Okay. Any suggestion or any answer for the first comparison the algorithm will perform? Can you just type in A1, A2? Okay. Any other ideas? By the way, I mean, I know that someone may have low grade for test number 1, okay? Remember that for this class, I will allow you to have some bonus points by finishing the programming that I have for the programming contest training. So just go to the website trend.selu.edu /domchurch that I already saw that a student, I think Jared Martin, right? He's on 2 out of 3 problems correctly. Very good. Yeah. So every problem you can solve there will have some bonus points. Yeah. I think 5 points. And that will help you to improve the grade in the class if you want to do so. Okay. So usually I will give students some bonus points if you want to improve the grade, the final grade. Now, now the first comparison will be here, A2 and A3. Yeah. Why A2 and A3? You need to work on the merge sort. A1, A2, and A3, right? So how does the merge sort work? Partition it around the middle, right? So here you have 3. 3 divided by 2 is 1. So that said, the left will have 1 element, the right will have 2, right? Sort the left, right? Sort the right, okay? So the left does not need to sort. The right will be sorted. And so it means that we will break this one, right? The left does not need to sort. The right does not need to sort. So now we merge. When we merge, we need to compare the value, right? And that is the first comparison. Okay? So it's a little bit different than insertion sort. That's why I want to help you with the first comparison. So if you understand it that way, you can continue to finish the decision tree. Okay? So hopefully you can finish here for 2 sorting algorithms. Any question? If not, then we will stop here and see you next week. Okay?